The tank is horizontal and works by gravity. Water or oil can be used. Colored emissions, oily or watery, permit the visualization of the flow around models fixed between the walls. These two walls are separated by a distance of about 1 millimeter. A first test section permits simple flow studies. For instance, the viscous flow around a profile at incidence. There is no separation and the local flow turns around the trailing edge. It is the same at low speed around the step, the axial symmetry of which determines that of the flow. At high speed, a separation zone develops upstream of the step. There is a vortex and three-dimensional effect. Same flow evolution at the base of a downstream facing step. At low speed, no separation. At high speed, there is separation at the base and reattachment downstream at a small or zero angle. A second type of test section permits the visualization of two flows meeting on an obstacle. The separation line between two streams of different velocities starts from the obstacle at a near zero angle. This angle is practically a right angle if the velocities are about the same. These last two examples are part of a study concerning separation angles carried out in this narrow tank. The water tunnel is vertical and works by gravity. A tank of about 700 liters provides a useful test time of 2 minutes approximately and the flow velocity of 10 centimeters seconds in a square test section. Many sorts of models may be used and their mounting is according to the studied parameters. Half wall-mounted models such as this ellipsoid equipped with a variable instance device. Two-dimensional models such as this ground effect machine equipped with a ducted fan and studded with a movable plate simulating the ground. Complete models such as this wing fuselage combination mounted on an articulated support so as to allow for instance variations or side slip during testing. Two-dimensional separation study. The pattern of the streamlines, velocity profiles, separated zone of its boundary may be obtained with precision by the processes used. For example, in the case of a 15% thick profile at zero incidence, the streamlines show up if air bubbles are used. Only a few bubbles from downstream get into the separated zone. The structure of this region shows up due to the lacteous emissions. Three-dimensional study of separation. The streamlines are visualized by colored emissions. By reducing these emissions, the flow along the wall appears, and the separation line in particular. In the case of an oblate at an incidence of 6 degrees, the colored thin streaks represent the streamlines of the external flow over the upper surface. By cutting down progressively the importance of these colored streaks, it is possible to visualize the boundary layer flow nearer and nearer to the wall. When it is all cut off, The flow along the wall can be visualized and the separation line at the same time. The vortices can be visualized very easily either by means of colored lacteous emissions or by means of air bubbles. Tipped vortex of a rectangular wing at incidence. In this side view, the helicoidal structure appears clearly. Tipped vortices of a canard at incidence. These tests gave precise trajectories of the vortices for various model configurations and showed clearly the interaction effects between the canard planform, the wing, and the fuselage. In this particular case, the model is seen from above, and the incidence is 12 degrees. Apex vortices on a thin delta wing. Incidence 12 degrees. With a mirror placed downstream on the wing axis, we can visualize the flow when it crosses a thin lighted cross-section, first at the 50% chord location, next at the trailing edge. Air bubbles help to locate the vortices and their rotation. They also make possible a reconstitution of their trajectories in three-dimensional space. At high incidence, turbulence downstream breaks up the helicoidal winding and initiates a real burst of the core in pockets of turbulent fluid. In this test, vortex axis is evident due to a red emission near the apex. The bursting of the vortex starts a diffusion, due to which the color becomes green, making the localization of the phenomenon much easier. In this manner, it has been possible to locate easily the bursting point and to notice its displacement in function of the various parameters, for instance, in function of side slip, as can be seen. A circulation increase around the profile due to blowing gives first a displacement of the stagnation point and the bubble at the leading edge. Next, no separation zones near the trailing edge. In this first example, blowing is taking place tangentially over a lowered flap. In the second example, the same result is obtained by means of the jet simulating a pod-mounted turbojet exhaust. In fact, a small deflector drives the jet towards the flap, provided with a slot, allowing the jet to reach the upper surface and to flow downstream over it. In the case of a zero-instance profile, activating a very inclined jet at the trailing edge gives a similar evolution apart from the curvature of the fluid flap due to the flow action. Grouping the leading edge permits here to adapt the profile shape for the flow by reducing the leading edge bubble. Same test on a rectangular wing of limited span seen from the tip. The fluid flap initiates a tip vortex as if incidence had been increased. Same thing when we look from above the wing. A last example in the case of a delta wing with fluid flap. It proves that blowing is an efficient device to control the boundary layer and to provide hypercirculation for all planforms. In the case of a jet wing, coming close to the ground gives, first, a favorable effect, which is maximum when the jet reaches the ground, and next, a sudden drop in circulation because of a flow blockage under the lower surface. In the case of a platform supported by jets at the leading and trailing edges, two vortices under the lower surface are typical of the hovering condition. The flow pattern when the platform moves forward is notably more complex. Upstream of the first jet, a typical ground effect vortex can be noticed. In the case of a central ducted fan platform, there is a spreading of the jet in the hovering condition, and the ground effect vortex is initiated by a forward motion. The same phenomena can be observed in the case of a three-dimensional model when hovering and in forward motion. The disappearance of separation at the rear of a streamlined body when an axial jet is used shows the importance of the interaction effect between the external flow and the turbojet internal flow. In this test, a separation no longer exists, as can be seen due to the colored emissions nearer and nearer to the wall. Same test in the case of a cylindrical fuselage with a base at right angles to the axis. The jet reduces the rear separation to an annular zone where a torus-shaped vortex can be seen. Same type of phenomenon in the case of a fuselage equipped with swept-back and sharp-tipped fins. The jet has an important effect on the flow around the tail. A last example deals with simulating a running turbojet in a complete airplane that we can see from various angles. Here's a view from above. Then a side view. Starting the engine shows neatly the interaction between external and internal flows. On this composite picture, the air bubbles show the flow from under the plane, bottom picture, and from the side, top picture. This rear view shows particularly well the jet induction effect. This free surface tank is horizontal and works in open circuit. Several nozzle blocks can be used. The flow around the models is visualized by two optical methods. The first one utilizes a flat tin bottom and is reminiscent of the shadow methods. The second one is reminiscent of interferometry because of the bottom fringes. Starting the nozzle initiates the detect shock wave showing up as a wrinkle on the surface. On either side of it, clearer and darker zones appear. The same phenomenon visualized by the second method is marked by a displacement and a deformation of the fringes. The shock wave location is given by the line through the inflection points of the most inclined parts of the fringes. Wedge attached shock wave. The wedge is largely open and at zero incidence. Same flow visualized by the fringes method. Comparison with the flow around the sharp wedge. The model is still at zero incidence. Same test, but at incidence. In all the flows, expansion waves can be seen starting from the model tips. At the water tunnel, an apparatus has been developed to make possible an analogy study of thermal erosion in the case of simulated missile nose cones in a uniform water stream. The model is made of molded ice and is mounted on a support. The mold protects the model while the water tunnel and tank are filled with water. The mold is removed away from the model just before the test begins. The observations carried out during testing brought to light some interesting facts concerning the evolution of the contours and the ablation velocity in function of the various parameters studied. A conical nose experiences first a fast ablation velocity which quickly decreases. Next, this velocity tends to stabilize itself. The shape remains conical while getting flattened. The flattened forward portion of a cylindrical nose gradually tends to a semi-spherical shape. Its ablation velocity, relatively small, increases slightly during testing. The Rankine nose, the shape of which is given by the flow boundary of a point source in a uniform stream, has a stable shape and a constant ablation velocity. Increasing the stream velocity means an increase of turbulence in the separation zones. That means faster melting of the model in these regions. When the incidence increases, the model melts faster at the lower surface and slower along the separated zone of the upper surface. An hydraulic analogy approximating hypersonic flows around nose cones may be obtained by means of thin and parallel water jets, the velocity of which is given by measuring the pressure conditioning the jets. The model, lighted from behind by a directed beam, is placed under a rose from which water comes out. In this presentation, the flow is, as usual, directed from the left to the right. The analogy resulting from the Newtonian approximation lies in the fact that the hypersonic uniform flow is represented by the jets upstream of the shock wave. When the density and the velocity of the jets are high enough, these give a continuous liquid layer on the forward part of the nose, thus representing the shock layer. The liquid layer over a flat nose at zero incidence has very nearly a semispherical shape, which appears here in red because of a colored emission from the model's surface. Same pattern in the case of a slightly rounded nose at zero incidence. On this model, the incidence effect is very small. This is a test at zero incidence of a nose the contour of which is an hyperboloid. This shape leads to notable incidence effects. The layer is thicker at the lower surface and thinner on the upper surface. Testing a conical nose, the tip of which is spherical. There is a relation between the layer thickness and the radius of curvature of the tip. Obviously, this shape shows little incidence effect.